All right. I think it's working. But yeah, it's June, 10th week. This is our last week together. And then, and then some of you are graduating and will, exactly, right? Maybe that's the mood right now. Or not, I don't know. Okay, so we're talking PCA, and we left off. I apologize for the delay in getting all the notes and videos up, and the video recording app didn't work, last week. So I'm trying to find like my old video on the EM algorithm, which was probably a little bit different. But we left off on Friday introducing PCA, and we said we're taking this high dimensional data and we're projecting it down to a lower number of dimensions. And as far as visualizing this, it's really we're only able to like visualize projecting three-dimensional objects down to 2D or 1D, and maybe even like and I'll do an example where we're projecting a two-dimensional data set down into one dimension, okay? But I'll do an example, and I hope I've got time to get through it, where we can project like 700 dimensional data down to like 100 dimensions, and yet still preserve the kind of the key structures or variation that exist within the data, okay? Anyway, as far as the math goes, we said we want to find some kind of set of W's, okay? W's so that we will maximize the, what am I looking for? Okay, so when we multiply W against our original data Y, this will be the projected data, and we want to do it in such a way that the variance in the projected data is maximized. Okay, so we want to find a set of W's that are uncorrelated, so that when we multiply W times Y, the result will be X, and the variance in X is maximized. And in order to do this, we find that the variance can be expressed this way, and in order to kind of maximize it, we want to pick our W's so that that they are the eigenvectors of the covariance matrix C, okay? So when we say, so we found an expression of the variance of our projected data, and we said it's going to be W times the covariance matrix of Y times W, and if we take the derivative of that and maximize that, with the constraint that our W's have some limited size and they don't just, because if we said we just want to maximize this thing, we can just pick W to be as large as we possibly want, right? Like W is like a, infinity. But we give it a constraint that says, W's can't be unconstrained, they have to be a limited size. And so when we set that constraint, the W's that will maximize the resulting variance of our projected data will be such that they fulfill this equation, which is the covariance matrix times W is equal to lambda times W, okay? And we recognize this as kind of the solution for eigenvectors, and we say that if we find the eigenvectors of the covariance matrix C, then the eigenvectors will fulfill this equation, and thus if we want to maximize the variance in our projected data, the way we're going to do this is find the covariance matrix of our original data, take the eigenvectors of that covariance matrix, and use those resulting eigenvectors, okay? And those will be the directions, the W's, so that we can produce our data X, okay? Which will be just W times Y, right there. Is that okay? And let me just kind of summarize this with a quick Notepad. Okay, so we're going to say we want to transform y into x, okay, and we're going to say x is equal to basically, what are the dimensions? So y is n by, I forget what letters I used. Okay, yeah, y is m-dimensional and we want d-dimensional, right? So we're going to get y, and we want to find our w's. W is going to be m by d, so that, you know, x is going to be n by d, where d is less than m, okay? So we want to figure out what our w is, and we find that we want the variance of x to be maximized, okay? And we say the variance of x can be expressed w, so just if we do the first direction, okay, x, you know, in the first principal component, can be expressed with this, okay, so the derivation is on Friday. C is the covariance matrix of kind of your centered y. Okay, and then and then to maximize maximize sigma squared leads to covariance matrix times W is equal to lambda times W, which tells us, you know, I should put little arrows over everything. W is an eigenvector of C. Okay, so this is kind of where we left off, and then and I guess I'll do this just with kind of a brief example, right? So what we are effectively going to do is, and here's a kind of a neat illustration, is if you've got two-dimensional data, we want to kind of project it down to a single dimension that captures the most variance, okay? And so for these purple points, the direction that captures the most variance is going to be, this is our first principal component. And that's effectively, I've written a little bit of code, and I don't know if you guys started homework 6, but homework 6 will basically walk you through kind of these steps. You'll do it via the covariance matrix. The correlation matrix is the same thing, except you've kind of scaled everything down so that they all are, they've been standardized. And then you can also do it via SVD, which, you know, we don't have to worry too much about. So basically, I've created just some data here, okay, two-dimensional data, and what we want to do is we want to project this down to one dimension, okay? And so what this is going to end up looking like is we're going to kind of take this picture here, and we're going to say, okay, how do I maximize the variation that appears here? And I think we're going to say, like, it's going to look, well, that's not very good. Something like this, and each of these dots are going to map onto onto this direction here, okay? And so our resulting data set, let me get some points that are really close, will basically just look like dots along a single line, okay? If we project it down to one direction. Okay, so this is effectively what we're going to do. We're going to take our data and try to project it down here. Let me just kind of, this is the original data over there, and this is what we're going to do, okay? Okay, so to kind of illustrate this, so here's our data here, and what I'm going to do is I'm going to take, right now I have it just stored as x. This is the original data, x. And I'm going to go ahead and I'm going to center this. Okay? Oops. So, so I calculate the means of x, each column mean, and I'm going to just subtract those off from x. Okay? And so my centered x looks like this. And if I were to just plot, I don't feel like plotting it. All it does is just centers everything so that the mean of here is 0 and the mean of here is 0 over there. Okay, and I can just kind of verify and just see, you know, are the means of my centered data 0? Indeed, they're practically 0 on the order of 10 to the negative 16. So I think we're fine there. And we're going to find the covariance matrix of this thing. Okay, so this is effectively my matrix C that you know, that we kind of worked through here. So I've effectively, you know, we've centered the matrix, and now I've got the covariance matrix C right here. And I'm going to go ahead and I'm going to find the eigenvectors of this. All right, and this is very simple. In R, you can just ask for the eigenvectors of XC. If you, I don't want to try to do this live, but if you had to find eigenvectors by hand, you would have, you know, you'd find like the characteristic equation of the matrix, and solve for that, and you would do it that way, right? But anyway, we can just ask R to do eigen of the covariance matrix. We've got this 2 by 2 matrix here. We ask for the eigenvectors there, and here's my first eigenvector. Let me make my screen size, the font size bigger for you. I need to restart R just to make my text bigger? Okay, I guess. Oh dear. Okay. Oh, I posted this on CampusWire, but I don't know if you saw, but we got a response regarding why people's answers are different, and what happened was that in version 3.6.0 they changed the behavior of the function sample, okay? And so so if you've upgraded to 3.6.0, and I'm always an advocate of upgrading to the latest version, because usually it's because they'll fix bugs, but apparently in the older versions of sample, and they got all the way through 3.5.3 and nobody noticed, really. I mean, not nobody noticed, but like it wasn't a big issue, but sample was not performing in a uniform manner. You know, we assumed that random sampling in R performs uniformly, and there was a small issue in the way it ran, and it was not performing uniformly. And so they fixed that in 3.6.0, but then that made everything work out differently than before. And so if you want the answers to match before, you can change it to use the non-uniform sampling that existed in 3.5.3 and older versions of R, but probably not recommended. But anyway, okay, so here's our covariance matrix after we've centered our data, and now these are the eigenvectors. Now the thing about eigenvectors is that the signs don't matter, but I will go ahead and I'll just use these as is. I think what's going to happen is if I project this data down onto the eigenvectors, it's going to well, let me just multiply it by negative q, okay? And what we will see is if I project it down to the negative q, all it's going to do is it's going to just kind of take our data, project it down onto actually in both directions, and it's going to effectively just rotate it so that the axes align with the direction of greatest variance. Okay, so we get that, and then when I project it, all it has done is it has just kind of rotated the data so that it aligns in the direction of greatest variance. Okay, so you can kind of see it's just this exact same data. You can even kind of see this little funny, almost looks like a J. That exact same structure remains in the data here. Okay, except if I use the eigenvectors produced by Eigen, you get the inverse of this. It's negative, and so it's going to be the exact same thing, but just kind of flipped. Okay, so this is what it ends up looking like. That J appears over on this side now. Okay, so all we're doing is we're just projecting the data down into kind of the direction of greatest variance there. Okay. And so now that we've got this, this preserves the entire variation of the data set, okay? By keeping both principal components, we've preserved the entire variation that does exist in the data set. However, we've done it in such a way that the first direction has maximum variance. And this allows me to just keep only one of these principal components, and I've still maintained a lot of the variance that exists in the data, okay? I'm not going to have all of the variance, but I will still have a lot of it, okay? And so projecting this down onto one dimension is just basically, you know, using, shining a ray of light from up here, I guess parallel rays of light, so that they just drop down, okay? And so all I'm going to do is I'm going to just delete or just keep the first column after I've projected the data, okay? So the way I've projected the data is I've just taken kind of our original data, our data after I've centered it and multiplied it by our projection, kind of the eigenvectors, which I've called Q here, okay? And so that gives me kind of PC, the principal components. And now I'm going to just keep the first column, and so here, all I'm doing, so if this is both principal components, this maintains the entire variance that exists in our data, and all I'm doing now is I'm just keeping the first column, okay? And so if I plot this, I'm sorry, that's the first principal component. I don't even know if it's worth plotting this. I can do this is just what the data looks like when you project it down to one dimension. It looks uninteresting, okay? It manages to preserve a lot of the original structure though, okay? In that even though I've kept only one direction, I can project it back, okay? I can take our data and multiply it by the transpose of what I used to project down, and this will kind of recreate our data in 2 dimensions, okay? Display list redraw incomplete, I don't know what that means. So let me delete this plot, delete this plot. Okay, so here's kind of our original data, and then I projected it into the principal components, and let me just delete this. And if I project it down onto one dimension, basically you can see how it's taken these data points and it's just turned it into a single dimension. So yes, I have lost some of the information that exists in 2 dimensions, but it still it remains fairly faithful to the original data, okay? Because we've captured kind of the one direction that maximizes the variance that exists in the data, okay? So in order to express the full variance that exists here, we need both dimensions. We need the x and the y, right? Or we need, variable 1 and variable 2. And what I've done is I've basically projected it down onto one dimension here while maintaining a lot of the original structure that exists in the data, okay? And so this is effectively what we are doing in principal components. And homework 6 kind of walks you through, a few variations or a few different ideas behind this. But the idea is, again, here's your original data with all the variance. We are projecting it down into a single direction here. Is that okay? There's this cool website which kind of does a 3-dimensional example, all right? And so here is the data in 3 directions. And in order to kind of appreciate the full variation that exists in 3 directions, or 3 dimensions, you need to have a 3-dimensional kind of display of it, okay? And what we can do is, different projections of the data, like this is a valid projection. Like if somebody should shine a light down kind of from this direction, kind of pointing up, this is how the data would appear in one way. But this is not representative of the data. And so what PCA would do is it's going to say which direction maximizes the variance. And so we're going to kind of project it down from 3D into 2 dimensions, and to kind of maximize the variance captured in 2 dimensions, this is going to be the direction to project it, okay? And we can see that the first principal component actually captures the most variation, and PC2 and PC3 probably doesn't do a whole lot, okay? But that's what we have there. So you've got different things here. This is another thing where they've 17-dimensional data set, and this is what the original data looks like. If they project it down into kind of 2 principal components, what we see is that in one direction, regarding one of the principal components, Northern Ireland is vastly different from the other 3 regions of the United Kingdom, Wales, England, and Scotland. And upon closer inspection of the data, it seems to be that the primary difference that gets detected is that this is how much food do they consume, and it seems that in Northern Ireland, the amount of fresh potatoes they eat is much greater than the other 3 regions of the United Kingdom. And that seems to be a significant contributor towards its kind of outlying nature regarding the other nations, or I don't know, what do you call it? Countries within the UK? Are they countries? England counts as a country, and Wales counts as a country? I don't know. I'm not sure. They don't get their own seat at the UN, though. So I don't know, but anyway, okay. Let me do this thing. I think I've got enough time. Start in a whole instance of R, that's fine. Okay, so what I have here is I'm going to load up an image of Audrey Hepburn from Breakfast at Tiffany's. Okay, this is the image here, and this image it's in black and white. Okay, so there's only one kind of color channel, not even a color, but it's black and white. It's 634 pixels by 791 pixels. Okay, and so we're gonna kind of represent this as a matrix. And we can kind of treat this, each column, each of those 634 columns, as a dimension in a vector. So we can imagine having kind of 791 row vectors, and each vector exists in 634 dimensions. Okay? And so we can kind of imagine it that way. When we load up the image and take this, it's got... that's what it says. 634 columns, 791 rows, one, I guess, frame of time in case you have like a GIF or GIF where you have multiple frames. And then there's technically 3 color channels, but a black and white image, the red, green, and blue channels all have the exact same values. And so I'm going to just take one of the channels and one of the only time frame, and we will do this. And you can ask R to plot this, and it will look like so. Okay. And so what I'm going to do is I'm going to take this matrix, which we have called AUD for Audrey, and if I ask for the dimensions of this, it's 791 by 634, and what I'm going to do is I'm going to go ahead and I'm going to just subtract off the means of each column. Okay, so I'm going to center my matrix so that each column has a mean of 0. Okay, and I can just kind of check to make sure that after I centered it, all of the column means of my centered matrix is equal to 0. Okay, and I can do that, and when I do that, it comes back and it says true. All right, and if I were to kind of plot this, okay, this is what it looks like. When you take each column and subtract off the column mean, what we end up is getting this streaky image. So that with vertical streaks, because basically the image is represented with these columns, and so this column happens to have, I guess, a lot of, in the original image, in this vertical line of the image, there's quite a bit of black here, and so the overall mean of this column has high. So black values, I think, have high values or low values, whatever it is. You know, we're centering it, and so that this streak right here kind of ends up being quite gray, whereas you know, this portion of the image has a lot of white, and so you know, it subtracts a different number because you know, the mean of this entire column is different. Okay, so we end up getting kind of this streaked image where, like, if we took the entire mean of the column, they would all end up with the same kind of grayness value. Okay, if we were to add up the entire column there. Okay, so so how do I do this? Well, what I'm going to do now is I'm going to take this centered matrix, and I'm going to calculate the covariance matrix of it, okay? The covariance matrix of our centered data. And so the dimensions of our covariance matrix is 634 by 634. It's a very big covariance matrix because there were 634 dimensions in our original data. So, so anyway, that's what we have. I'm going to go ahead and I'm going to ask R to calculate the eigenvectors of this covariance matrix, this 634 by 634 covariance matrix, okay? And it does that. And so how many eigenvectors exist for a 634 by 634 matrix? 634, right? So you're going to end up getting a whole bunch of these things, but they're going to be kind of ordered in a way that the first eigenvector captures the most amount of variation and the other ones capture kind of less. And so we can see that, you know, if I ask for what does the results of this eigenvector decomposition give us, you know, we've got 634 eigenvalues, and then the eigenvectors is a 634 by 634 matrix, okay? And so what I can do is I can just choose to keep like the first 50 principal components, okay? So I can just, so rather than keeping all 634, or I shouldn't call them principal components, but okay, rather than keeping all 634 eigenvectors, I can just choose to keep the first 50, okay? So I'm going to take the eigenvector matrix, which is 634 by 634. I'm going to just take the first 50 columns. So the result will be that this will be 634 by 50, okay? And then I'm going to take our centered matrix and multiply it by these kind of first 50 eigenvectors. Is that all right? Okay. So the original data, the dimensions, or I guess our centered data, the original data is 791 by 634. I've just multiplied it by a matrix that's 634 by 50, so that now my new data, after I've projected it down, is 791 by 50, okay, my projected data. Now, if I were to try to plot this projected data directly, it's not going to make any sense at all, okay? Okay, it's 791 pixels or rows by 50 columns, okay? This doesn't look like anything, all right? We cannot make sense of it, okay? However, we can take this, which is now 791 by 50, and I can kind of reverse or reconstruct the original 791 by 634 structure by multiplying it by the kind of transpose of those eigenvectors, okay? So I'm going to take my projected data, which is 791 by 50, and multiply it by the transpose of the eigenvectors, and this will be my kind of reconstructed image. Okay, so rather than, this would be like this, like a weird kind of compression system where the original image is 791 by 634, but we somehow compressed it down to 791 by 50, and this is going to be the kind of the package that we can send, which, you know, is like 1/12 of the weight. Like, imagine each of these pixels costs $1 to send or something. Okay, you can send all of these over at, you know, 1/12 of the cost, and then over there you give them instructions on how to kind of reconstruct the image. Okay, so so we do that, and so when I reconstruct the image, this returns it back to 791 by 634. Okay, and then in order to kind of get the original image back, I have to add back the column means, which I will do here. And now I can plot the reconstructed image, even though this is reconstructed from 50, kind of 50 columns. We've taken our 50 columns and reconstructed it back to 634 columns. And this is what our image looks like. So let me just kind of give you a direct comparison. Let me delete this, and we'll delete our streaky image. Okay, so this is the original image with all 634 columns, and then this is the image after we deleted, like, I don't know, a whole lot of these the values, right? So we projected from 634 down to 50, okay? And we're going to pretend like we transferred this much smaller version, and then from there we reconstructed, or we tried to reconstruct the original image, and this is what it looks like. So is it the exact same as the original image? No, well, I don't know what it looks like up there. Let me see. Okay, you can see like a slight degradation in quality, right? So you can see we've lost some of the detail, okay? There's basically less contrast in the image, like our eyes can detect less contrast in the image because, you know, we've tried to kind of maximum variation in an image kind of represents high contrast, and what we've done is we've taken, we needed all 634 dimensions to kind of capture the full contrast of the original image, but we've reduced that down to 50, okay? And we have like a much smaller kind of package, but yet at the same time we can kind of reconstruct the original form of the thing and kind of compare what that looks like, and we can see that we've managed to preserve a lot of the original variation, okay? And so I just wanted to kind of do the same process, but what if instead of keeping 50 eigenvectors, I kept different amounts of eigenvectors? So I created a loop that does this, and we're going to go, I'm going to start off with keeping just one principal component, okay? So from 634, I'm going to just keep one. I'm going to do 1, 2, 3 through 10, and then I'm going to just kind of increasing my intervals, 12, 14, 16, 18, 20, and then count by 5s, and then count by kind of 10s, 20s, and get up to, you know, 500 principal components. So I'm going to kind of run through this, and I think this works. And we can kind of see what the our reconstructed images look like if I only keep a few of these principal components, okay? So again, what has happened here, so this is, so here's the original image, okay? If I, so this is 791 by 634. Here I've reduced it to 791 by 1, okay? All right, so I've thrown away a ton of the information. And it says, well, in order to kind of capture the most amount of variation that exists in the data, this is the result, okay? And it's actually like, this is you have no idea what this image is, but if you look at the original image, you also see there's like some things, right? There's like this big patch of white here, and then the table area is a little, is whiter than the rest, and the rest is kind of dark. And so, so it has kind of sort of managed to try to capture something like that, okay? If I bring in a second principal component, it starts to bring in a little bit more structure here, okay? So again, here's the original data with two principal components. It looks kind of like this. If I add, and then, we start to see some of the shape here, and, there's a little bit more, like, just look for, like, patches of white and black, okay? In the original image, this is what we had, right? Very white right there, very white right here, very dark here, and very dark up at the top, okay? So kind of look for those things. So one PCA, here's with two, here's a third one, okay? Third kind of eigenvector kept in here, and then with the fourth, and we're starting to, again, get some structure here, and we get, we see these kind of dark patches down here, and if we look at the original image, oh, indeed, we can see, okay, this kind of corresponds to, I guess, her elbows or dress or something, and something down here, and that structure begins to form here, okay? And so at 5, and at 6, now we get something, you actually begin to see like features of a face, okay? You probably have no idea what image this is, but somewhere along, here's 7, 8, 9, and 10, and this is like, I don't know, some deep fried image that, you might, if somebody gave you this thumbnail and asked you, like, what is this thing? Some people might recognize, because it's such an iconic photo that they might start to recognize what this might look like, right? And then at 12, you know, I don't know at what point, here's 18 principal components and here's 20. I think we could recognize that this is Breakfast at Tiffany's, right? And so, and as I increase, here's 25 principal components and here's 30. What we see basically is that we are able to capture more of the variation in the original image, which when it comes to a black and white image, basically corresponds to more contrast in the image, okay? And so here's with 30 principal components, 35, 40, and 50, 70, here's 90, I don't know what's going on with my computer here. Okay, 70, 90, 120, okay? And I would say at 120, it's difficult to really see any huge improvements here, okay? So here's 120 and 150, and I don't know if you can really see any difference here. 180, 210, it all kind of looks the same. 300, 400, 500, okay? So we're not getting too much improvement by keeping way more principal components here, okay? Now, maybe from a concept, it's kind of cool, like, oh, we can compress an image down. Nobody uses this for image compression because the computational workload of finding the eigenvectors, transforming the data down into these principal components, and then undoing the transform by multiplying it by the kind of reverses is like just too expensive to do, and so we don't use this as like a way to compress images. But in theory, it could be done, okay? But just because it could be done, that doesn't mean it should be done. But I thought this was kind of just like a neat, I don't know, a play experiment where we're taking this high dimensional data, which exists kind of in the form of this image matrix, 791 rows by 634 columns, and we can project it down into basically another matrix that is, you know, 791 by 50 and still maintain a lot of this structure in the original data. So anyway, you'll cover PCA in your last homework. It's a little bit more like a tutorial. Shouldn't be too bad. And so we'll end there, and we'll see you guys on Wednesday.